So for our class, for scatter plots, we can never say causation exists. And we kind of talked about this in chapter 1. We can't say that one thing caused another to happen. All we can say is that they're related to each other. So we can say that there's a positive or negative linear association. So association means, yeah, they have something to do with each other. Causation is a much more bold statement that we cannot just assume. So in other words, we cannot say that one variable increasing causes another variable to increase or decrease. We can only say that the first variable is associated with the other variable. So whatever your x is associated with whatever your y is. So we can say that the speed of the club head has a positive linear association or relationship with the distance the ball travels. We cannot say faster club head speeds cause the ball to go further. And the book talks a little bit about why not, and that's because the simple, quick answer is other variables affect the distance the ball travels. It's not just how fast you swing. There's wind, there's skill level, there's the type of club you use, there's all kinds of different factors. So other variables affect the distance the ball travels beyond just club head speeds. And that's generally the case. If I'm trying to show the relationship between two variables, it's not just those two variables that we're talking about. It's a lot of other things that cause things to happen. So we stick with the words association or relationship. We do not use the word cause. We do not say one thing causes another to happen. All right. The video reset itself, so I'm just going to keep on going. So moving on to section 4.2. Still going to use the same golf data as we go through 4.2. This is called the least squares regression line, and I'll explain why it's called that. You don't really need to know why it's called that, you just need to know how to use it. So the least squares regression line is an equation for a line that goes through the center of the scatter plot to help predict outcomes within the domain or scope of the given data. It's kind of a long sentence, but I'll break down each part of it. So it's an equation, just like in algebra. It's for a line that goes through the center of the scatter plot. We'll talk about what the center means for a scatter plot. And it's used to predict outcomes within the domain or scope of the given data. It's more commonly known as the line of best fit. So again, you might have studied this at the high school level or middle school level, line of best fit. So it's a line that goes through the scatter plot in a way that minimizes that the distance between it and the data point is minimized. So that's why they call it the least squares regression line. They're trying to find the tightest fit. So if you look at the picture below, the distance between each data point and that line is as small as it can get. We want a tight fit in that data. So we move that line around until it's as close to all the points as possible, and that's why it's called the least squares regression line. So it always goes through the mean or average for each variable, the x bar and the y bar. We call that the center of the data. So if we were to take all the x values and average them, x bar would be somewhere here. And if we were to take all the y values and average them, the y bar would be on the line as well. So the very middle of the scatter plot, the average of the x values and the average of the y values, is where that line of best fit goes through. So it always goes through the x bar, y bar, the mean of each variable. And one more thing we want to talk about before we get into how to calculate this is the vertical distance between a data point and the least squares regression line is called a residual. We'll talk a little bit more about that in a few minutes. So the vertical distance between a data point and the least squares regression line is called the residual. And so that's that distance here. And again, we'll talk about that distance in just a little bit. So it's the line of best fit. Again, you might have studied this. If you have your data points, you try to find the line that minimizes the distance between the data points and the line itself. Alright, so the reason the line of best fit is called the least squares regression is because it minimizes the sum of the squared residuals. So if we take this distance, all the positive and negative distances between the points and the line, if we took all those distances and squared them all, kind of like we do for standard deviation, square them all so they're no longer negative, and add them all up, we want the smallest sum possible. So it's called the least squares because we square all those distances, and regression. Regression is a process for coming up with this line of best fit. And so least squares regression line. It minimizes the sum of the squared residuals. You don't really need to know that part. I just want to explain the name because I know it's kind of confusing. Alright, so this creates a line that can be used to make predictions within the domain of the data. So we can make predictions between the lowest x value and the highest x value. I cannot make predictions beyond the highest x value. I cannot make predictions beyond the lowest x value. So all my predictions have to fall within the scope of the data. Beyond that, I can't tell you what's going to happen. So we have the equation y with a little triangle on top. That is called y hat equals b1. b1 is a value times x plus b naught, and b naught is a value as well. So b1 is the slope of the data, which in algebra we call m, and b naught, b with the little 0, is the y-intercept. Again, just like in algebra. So we have, it's just like the equation y equals mx plus b, if you've seen that one before. Same thing. The calculator calls it ax plus b. It doesn't matter what letters we use. The number attached to x, the coefficient, is the slope, and the number by itself is the y-intercept. So it doesn't matter what order you put them in, it doesn't matter what you call them, the number attached to x is always your slope, the number by itself is always your y-intercept. And we'll talk a little bit more about that as we break down this equation. So very similar to algebra. Alright, so how to calculate the LSRL. There's two ways to do it. Most of the time we have the raw data. So if we have the raw data, we can use our calculator, put the data in L1, L2, and go to stat calc option 4, just like we did before. The other option, if you only have the statistics from the data, you don't have the actual data, you must manually calculate it. So B1, the slope, is the correlation coefficient times S of y over S of x, which is the standard deviation of y, standard deviation of x. And B naught is y bar minus B1 x bar. Now these two equations are on your formula chart. You don't have to memorize them. It is a little tedious to use them, but it's just following a formula. So if you go back to page 1, so the equation of the least squares regression line, there's the equation, there's your calculation for B1, And there's your calculation for B naught or B0. So you have everything there. You have the equation structure, you have how to get B1 and how to get B naught if you don't have the raw data. So we're going to do the LSRL for the golf data. The first time we're going to use the calculator, and the second time we're going to pretend like we don't have the raw data and use the statistics, and that way you can see both ways to do this. So we already have our data in L1 and L2. We've already ran StatCalc4, so these are the numbers you should have. Notice the A is attached to the X, so the 3.1661, etc. is the slope, and B is negative 55.7966. So, using the calculator, we have y hat equals, I'm going to round that to 17x minus 55 point, I'm going to make that 80. So the homework will tell you how to round. I'm going to round to the nearest hundredth. So 3.17 if we round, and negative 55.80 if we round. Now let's pretend that we don't have the raw data. We don't have anything in L1 and L2. We're going to say we just have the statistics. So on some of the homework problems, they're just going to give you x bar, s of x. If you go down, they'll give you y bar, s of y, and I believe they give you the r value. Somewhere in there. Should be. Oh, they don't give it to us, but we have it from before. Alright, so we know the R value is 0.94. The homework will give that to you if you need it. Let's say they gave us X bar of 101.875. S of X is 2.30. I'm reading these from the calculator, but normally you won't have these in the calculator. You'll just have them given to you on the homework problem. I'm just writing them down so we have them for reference. Okay, so let's pretend like we have nothing in the calculator and that the homework gave us all this information. So let's say all of this is given to us and we do not have the raw data. Which I think there's at least one homework question like this, where you don't have anything but these 5 numbers. So we're going to use these statistics to calculate B1, which is R 0.94 times S of Y divided by S of X. So again, that's pretending that's all we have. We have nothing in the calculator. So we're going to just crunch these numbers. We're going to do 0.94 times 7.74 divided by 2.30. Just throw those right into the calculator and you get your result. 3.16. I'm just going to round to the nearest hundredth to keep it easy. So pretty close to what we got in the calculator. The homework knows that you'll be a little off if you're given rounded values. No big deal. And then B naught is y bar, which is 266.75, and I'm reading these formulas off the formula chart. So 266.75 is y bar minus the number we just got, 3.16, times x bar, which is 101.875. So if I put all of that in the calculator, just crunching the numbers here, 266.75, sorry about that glare. Sorry, let's get this light turned off. There we go. 266.75 minus 3.16 times 101.875. And you get negative 55.175. So again, pretty close to what you get using the raw data. So on your homework, sometimes it will want you to manually calculate it this way. Sometimes you can just use your calculator if the data is in L1 and L2. There's 2 ways to do the same thing. Oh, B naught, right? B naught. So B1 was the slope, B naught is your intercept. Alright, so we're going to use the calculator, LSRL, we're going to use this one to make predictions. Y hat, The little hat means it's predicted. So that's your prediction equation. This is used to make predictions. And then we also have the raw data that we gathered, or that the textbook gathered for us. All right, so using the LSRL to make predictions, we can only use it within the domain of the data. So what is the predicted distance for a club head speed of 104 miles per hour? The first thing we need to go do is go back to the raw data and look at the x values. Is 104 within our domain between 99 and 105? So 104 is in our domain, and that's good. That means we can make that prediction. So we're going to do y hat equals 3.17 times 104 minus 55.80. So we're going to actually crunch that number. So 3.17 times 104 minus 55.80. Type all that in. We get a prediction of 273.88. And that is a predicted y value given that x value. Part B says, what is the predicted distance for a club head speed of 80 miles per hour? Now, yes, you could plug in 80, you could get an answer, but 80 is not in our domain. So because 80 is not within, not between 99 and 105, not between the lowest and highest x value, 80's way past our domain, we cannot use this LSRL. So it cannot be calculated. So you have to make sure that whatever x value they're giving you is within the domain before you crunch the numbers. Another part of using LSRL is computing residuals. So this is compute the residual for a given input. It says compute the residual for a club head speed of 103 miles per hour. Now the residual is the difference between the observed value and the predicted value. So the observed value is from the data, and the predicted value is from the LSRL. So the first thing we need to do is figure out the predicted value. The data table tells us that when the club head speed is 103, the data we got was 274. So this is what we call the observed data. So observed came from the data table. It was 274. And you might want to make a note that it came from table 1. The predicted y value is y hat. So we're going to do 3.17 times the x value they gave us. And we're going to come up with what we call a predicted y value. So 3.17 times 103 minus 55.80. So 270.71 is what we call the predicted value. So what we observed was 274 from the data table. What we predicted with the LSRL is 270.71. And the residual is always observed, which was 274, minus predicted, which is 274 minus 270.71, 3.29. This is a positive residual, which means what we observed is higher than what we predicted. So it's a positive difference. So what happened went over what we predicted. So if it's a positive residual, it's the observed is above the prediction line. If it's a negative residual, it's below the prediction line. So if we go back to our scatter plot, and explain that one more time. If we have our line of best fit, any data value below the line of best fit is a negative residual. It's below average. And any data value above the LSRL is a positive residual, which is above average. So below average if it's negative, above average if it's positive. All right, last thing for 4.2 is interpreting the slope and the y-intercept for a set of data. So the slope of the LSRL tells us how much the response variable y increases or decreases, if it's positive or negative, when the explanatory variable x increases by 1 unit. So for the golf scenario, for every 1 mile per hour faster the club swings, that's your x value, the distance the ball travels increases by approximately 3.17, and you have to check the units. I believe it's in yards and miles per hour, so you have to check those units to interpret. So for every 1 mile per hour faster the club swings, the distance the ball travels, which is the y variable, increases by 3.17 yards. The y-intercept, so that's just like algebra, that should be no big deal. The y-intercept of the LSRL is only appropriate in some scenarios. It tells us where the response variable, y, starts when the explanatory variable x is 0, which sometimes doesn't make sense or is outside the domain. So you have to kind of think about this one. This one's a little trickier. So for the golf scenario, it does not make sense when the ball will travel negative 55.80 yards. So it doesn't make sense for the ball to travel a negative direction because if our x variable, club head speed of 0, so if we're swinging 0 miles per hour, the ball's not going anywhere. So it doesn't make sense for the ball to be 0. Also notice that 0 is well outside of our domain. So we're talking about 99 to 105. Thinking about 0 is so far back, we can't know what's going to go on. So your book talks about if 0 is outside of your domain by a lot, then it doesn't make sense to interpret it. So this one's a little trickier. You have to decide if the y-intercept is appropriate for the given scenario. Sometimes it is, sometimes it's not. And that is it for Chapter 4. Those were the only 2 sections we covered for Chapter 4.